Alright, as promised, I have a capacitor problem for you guys. It's a similar setup to the examples we've seen so far. We have a 10-volt battery, and then a 15 microfarad capacitor, and then two parallel paths, one with a 5.2 microfarad capacitor, and the other with 12 and 8 microfarad capacitors. And our goal is to determine the charge on and voltage across each of these capacitors. When doing circuits problems like these for capacitors, we have a few general steps. So kind of our overall strategy that we're going to use, that is, first, find the equivalent capacitance using our series and parallel rules. And the second step is use Q equals VC, our main formula for capacitor circuits, for the whole circuit to find the charge that leaves the battery. And then after that, we use our general circuit rules in some order, and that order will change from problem to problem. Our general rules over here that I've numbered, so later on you can see which one I'm using at each point in time. One is that charge is the same in series. Two is that voltage is the same in parallel. Three is that charge is always conserved. 4 is that each path through the circuit must spend all of the voltage that you get from the battery. And 5 is, again, Q equals VC, and we can use that separately for each individual capacitor. So let's work through these one at a time, with the first step being find the equivalent capacitance. So to find the equivalent capacitance, first we need to find two capacitors that are either in parallel, and our C parallel equation would be C1 plus, actually let's call these CA and CB so as to not confuse them with our 1 and 2 over in the diagram. And then for series, 1 over C series is 1 over CA plus 1 over CB plus, and so on for every capacitor you have in series. So we need to look at this diagram and find any two that we know for sure are in series or we know for sure are in parallel. So some people might want to say that C1 and C2 are in series. Close, but not quite. So things are in series if all of the charge that flows through one of them also has to go through the other one. So if we kind of follow along in this yellow-orange here, the charge that goes through C1, some of it will go through C2, but some of it's going to go over here through 3 and 4 as well. So we're not ready to combine C1 yet with anything in series. Another thing we could think of is maybe 2 and 3 are in parallel with each other, because we have this path over here through C2 and this path over here. C2 is on this side of the parallel path, but it's too early to combine C2 and C3 in parallel because C3 isn't the only thing on this path over here. There's C4 there as well. So you could say that C2 is in parallel with 3 and 4 together. But if we look just at C3 and C4, any charge that goes through C3 has no choice but to go through C4 as well. So the first step here is that C3 and C4 are in series. So I'm going to combine those two using the series formula, rewriting it a slightly different way, where we'll have C3-4, that I'll call it, the combination of capacitor 3 and capacitor 4, will be C3 to the negative 1 plus C4 to the negative 1, all to the negative 1. And if we plug in our values, our 12 microfarad for C3 and our 8 microfarad for C4, we get a value for C34, the combination of capacitors 3 and 4, of 4.8 microfarads. And now before, just a little while ago, or actually let's redraw the circuit now. It can be helpful to do this. So we've got still C1 up here, C2 down here. Haven't done anything with those two yet, so we can just connect them how they were before. But now we've combined C3 and C4 together into C34, which is that 4.8 microfarads, and C2 is the 5.2 microfarads. So as we slowly work this down to get to one single capacitance value, this is where we're at so far. Now we can see that C2 and C34 are in parallel. The charge has to split here. It can either go through C2 to get back to here, or it can go through C34. And there's only one capacitor on each parallel path, so we are good to combine them in parallel. So C2 and C34 are in parallel. So if we combine them, we're going to get what I'll call C234, or the combination of capacitors 2, 3, and 4, will be C2 plus C34, which, based on our numbers, C2 is 5.2 microfarads, C34 is 4.8 microfarads, so we get a value of 10 microfarads for C234. Now let's redraw our circuit again. Still have our battery, still have C1, and now C2 and C34 have been combined together into C234. Hopefully this is easy to see that C1 and C234 are in series with each other. So we can, again, use our series equation, rewritten in a slightly different way. C1, 2, 3, 4, the combination of capacitors 1, 2, 3, and 4, which that will be everything for this circuit. That's all of our capacitors. So that is the equivalent or total capacitance. Will be C1 to the negative first power plus C234 to the negative first power, all to the negative first power. And we get our equivalent capacitance is 6 microfarads. We're just to show you what numbers we're using. C1 is 15 microfarads, and C234 was this 10 microfarads. So we have found our equivalent capacitance. Step 1 is complete. Now I'm going to have to make myself some more room here. So we've done step 1 now, so I'm going to put our equivalent capacitance up at the top here. That was our 6 microfarads. Now we need to do step 2. There are a bunch of different ways to use the formula Q equals VC. And one of the ways is to use this formula for the whole circuit, which is what step 2 is. And how that looks in terms of the formula is we want the capacitance for the whole circuit, or the equivalent capacitance. We want the voltage for the whole circuit, or the battery voltage. And we want the charge for the whole circuit, the total charge, or the charge that leaves the battery. So we already know the voltage of the battery is 10 volts, and we already found out the equivalent capacitance is 6 microfarads. So we get a charge that leaves the battery of 60 microcoulombs. So 6 microfarads was our first answer, and 60 microcoulombs is our answer to step 2 down here. Now we get to step 3, the one that generally throws people off. We have to use our general rules in some order or another. So I'm going to walk you through the series of steps here, and I'm going to make it clear which steps or which general rules I'm using for my step 3. So everything down here is going to be step 3. First, we can think about QB leaving the battery. And by general rule number 1, charge is the same in series. Well, the battery and capacitor 1 are in series with each other. So that QB that leaves the battery has nowhere else to go but directly onto C1. So this tells us that the charge on capacitor 1 has to be equal to the charge that leaves the battery. That's that 60 microcoulombs. So Q1 is 60 microcoulombs. Then, now that we know both the capacitance and the charge for this first capacitor, now we can use, oops, that's not 2, should be 5. Step 5, Q equals VC for a single capacitor. So again, Q equals VC, and this time we're just talking about capacitor 1. So this is the capacitance just of capacitor 1, the voltage drop just across capacitor 1, and the charge just on capacitor 1. Well, we already found out that Q1 is 60 microcoulombs, and we already know the value of our capacitance for capacitor 1 is 15 microfarads. So we can work through the math here to find the voltage across capacitor 1 to be 4.0 volts. So there's 2 steps that we've done so far. Now we need to move on to the rest of these capacitors. One thing we could do here is use, let's go to this orangish yellow color. We could use our rule that for each path through the circuit, the total voltage, all of the voltage you get from the battery has to be spent. So let's look at this path through the circuit that I've traced out in orange. So general rule 4 here tells us that the voltage we get from the battery, VB, has to be spent along the way. So the first thing we encounter on this orange path is C1. So some of that battery voltage will be spent at capacitor 1, and then the rest of it has to be spent at capacitor 2. Because on this particular path through the circuit, there are only 2 places to spend our voltage, capacitor 1 and capacitor 2. Well, we know the battery is 10 volts, and we already found V1 is 4 volts. So this tells us that the voltage on capacitor 2 is equal to what's left, 6 volts. Now we can once again pull our Q equals VC out of our back pocket. Except this time We're still using it to talk about one individual capacitor, but this time we're going to use it to talk about C2. So that means the charge just on capacitor 2 is equal to the voltage just across capacitor 2 times the capacitance of just capacitor 2. Well, the voltage on capacitor 2 we just found. It was 6.0 volts. And the capacitance of capacitor 2 we already know as 5.2 microfarads. You multiply those together, and you get the charge stored on capacitor 2 is 31.2 microcoulombs. So now we know everything we can know about capacitor 2. I'm going to go back to, we'll say, green here. So now we're left wondering what happens along this other path. Well, this is where we're going to bring in our conservation of charge here. So at this junction right up here that I've circled in green, we've got charge coming in. We've got that whole 60 microcoulombs coming in, and some of it will go this way, down towards capacitor 2, and the rest of it will have to go this way. So some of it went down towards capacitor 2, and some of it is going to go towards capacitors 3 and 4. So I'll call that Q34, because capacitors 3 and 4 are on this branch. So the total charge, the charge from the battery, I don't know why it keeps doing that. I don't know how to make it stop. The charge from the battery is going to be equal to the charge that goes down the path towards capacitor 2 and the charge that goes down the path towards capacitors 3 and 4. So we know some of these numbers already. We know Q2, and we know the charge of the battery. So from this, we can find Q34, the amount of charge that goes this way towards capacitors 3 and 4, has to be 28.8 microcoulombs. That's 60 minus 31.2. Then, after this, we're pulling out an old rule again, one that charges the same in series. So however much charge goes down the path towards capacitors 3 and 4, that's going to be the same amount of charge on capacitor 3, and it's going to be the same amount of charge on capacitor 4, because capacitors 3 and 4 are in series. And that is, again, 28.8 microcoulombs. So now we can use Rule 5, Q equals VC for capacitor 3, so the charge on capacitor 3, the voltage on capacitor 3, and the capacitance just of capacitor 3. C3, we know its value from up here is that 12 microfarads. And Q3, well, we just found that in the previous problem, or the previous part. That's the 28.8 microcoulombs. And with a little bit of math, that can tell us that the voltage across capacitor 3 is 2.4 volts. Now for capacitor 4, we have a few different options for how we can do this. So the first one I want to show you is using the one rule we haven't used yet. 2, that the voltage is the same on any parallel paths. So here we have two parallel paths, one that goes through capacitor 2 and the other one that goes through capacitors 3 and 4. So that means the total voltage on one path, so the voltage drop across 2, equals the total voltage on the other path. But the other path actually has two capacitors on it. So between capacitor 3 and capacitor 4, the voltages dissipated by capacitors 3 and 4 must add up to the same voltage dissipated by capacitor 2, which would give us our answer that we wanted, that V4, the voltage on capacitor 4, is 3.6 volts. But in place of this, we could also use Rule 4. The voltage for any path through the circuit is, you have to spend all of the voltage you get from the battery. So this time, I'm going to be talking about this big outer path through the circuit. The path that goes through capacitor 1, capacitor 3, and capacitor 4. So whatever voltage we get from the battery on this path through the circuit, we can spend some at capacitor 1, some at capacitor 3, and some at capacitor 4. Well, we know the battery was 10 volts, capacitor 1 was 4 volts, capacitor 3 was 2.4 volts, and what this leaves us is, again, the same answer. V4 is 3.6 volts. Last but not least, we could have just used general rule 5 again. Q equals VC for an individual capacitor, meaning the charge on capacitor 4 is equal to the voltage across capacitor 4 times the capacitance of capacitor 4. Where Q4, we already found out up above, is equal to 28.8 microfarads. And C4, from up in our diagram, we know is, sorry, you guys got to stop me when I make mistakes. The charge on Q4, on capacitor 4, is 28.8 microcoulombs, my bad. And the capacitance of C4 is that 8 microfarads from our diagram above. And when we work out the math again, we will once again get V4 equals 3.6 volts. So hopefully this does a good job of demonstrating how we can use each of the general rules for the circuit, for capacitor circuits, as well as how we go about solving one of these problems in general. First, finding the equivalent capacitance, then using Q equals VC for the whole circuit like we did up here, and then using some combination of our general rules for the rest of the problem. That's it, and there will be a problem simpler than this, but similar to this on your midterm, so this will be a great problem to practice before then. That's it. Have a good day.